Hello, my name is Daniel Van Zant. Welcome to this episode of Radically Interdisciplinary. I am very excited to talk to Dr. Alex Ellery. He is a Canada Research Professor at Carleton University, Ottawa. He has a bachelor's in physics, a master's in astronomy, and a PhD in astronautics space engineering. He has private sector, public sector, and academia experience. His area of specialty is in space robotics, but his research activities span across space manipulators, planetary rovers, planetary drilling, in situ research utilization, biomimetics, and astrobiological instrumentation. He is the author of two textbooks, An Introduction to Space Robotics and Planetary Rovers. He heads the Center for Self-replication Research, and he is working on his first popular science title, Manna from Heaven, about deploying self-replicating machines to the moon to construct a solar-powered satellite fleet for global expandable clean energy. Welcome, Dr. Ellery.
Thank you. Thank you for having me.
Absolutely. And I always like to start off with kind of a fun question. And so there's so much science fiction where humanity is out among the stars. There's Star Wars, Star Trek. If I go to books, I could have an entire library full of them. Isaac Asimov's work, all sorts of things. What is the fictional sort of space future? Which movie or book or anything else that you would want to live in?
I'd have to say with that question, it would be Star Trek. That was extremely influential when I was young. I'm from the UK, as you can probably tell from my accent. Star Trek was a bit of a latecomer to the UK. I think it came in the maybe 1970 or something like that. And it coincided at the time that the Apollo missions were happening. So I was very, very young, and I don't remember anything about Apollo 11 or anything like that. I was too young. But the tail end of the Apollo program, I remember watching one of the launches. I don't remember which one it was. It was probably 16 or 17. And I was captivated by it. I saw this as a kind of like a step towards this amazing future of space exploration. Of course, Star Trek, combined that with Star Trek, and that was like a vision of that future long term, further ahead. And I was so captivated by it. I just wanted to be a part of that future. And that, so ever since I was very young, I knew what I wanted to do, that I wanted to work in space exploration in some fashion.
I'm so happy to hear that. I'm a Trekkie as well. Did you watch the Next Generation or the original one with Captain Kirk and all?
This would be the original one.
Okay.
Which I have to say is still far superior, but, I'm biased.
All right. Well, we've already had a controversial opinion this podcast episode. When I've sort of been explaining your work to other people, half as a joke, half not, I've been telling them that you're the guy who wants to disassemble the moon and turn it into robots. What would be sort of your summary of your work?
I wouldn't put it quite in those terms, and it's not quite that dramatic. But essentially you have the right idea. I mean, it's basically, well, you could argue that we're doing the same thing on Earth. We're essentially trying to disassemble the Earth by extracting various resources and then utilizing them for our own purposes. We would do the same thing on the moon, primarily on the surface rather than actually deep into the moon. So the idea is actually my goal has always been to figure out a way to basically industrialize the moon or colonize the moon or whatever term you want to use, settle the moon in a way that hasn't been happening. As I said before, I saw the tail end of the Apollo missions, and in my young brain at the time, I thought by the time I grew up, I'd be living on the moon or something like that. And it never happened. And that's great tragedy, because when I grew up, at least some members of my generation grew up with the idea that, shown by the Americans in the 1960s and 70s, that human beings can solve whatever problems they care to solve, whatever they put their mind to. And of course, when I was young, I didn't understand the political dimension of space exploration at the time. So from that perspective, this never happened, and I think that's a great shame. And so my goal has always been to try and figure out a way to get to the moon, consolidate humanity on the moon in a way that is actually at very low cost. And the current, big fly in the ointment is the cost of launch to the moon, or to low Earth orbit and beyond, in fact. Now, there have been moves to try and reduce those costs, but the reduction of those costs are primarily to low Earth orbit. We're not talking about GEO so much, and we're certainly not talking about the moon very much. So I was trying to find a way around this launch cost problem, and so the obvious one is in-situ resource utilization, which basically means utilizing the resources that are there on the moon to build an infrastructure. And I've always seen it to not just as a means to an end, but as a means of building essentially a pioneer society on the moon who aren't reliant on Earth. I mean, we can go back in Earth history and look at the relationship between the United States and the United Kingdom, or Great Britain as it was then, and the various fractions that caused with tea parties and whatnot. So I've always been cognizant of the view that any kind of like a future lunar community will have to be self-sufficient. And so I've been trying to push that scenario as far as possible. As a natural kind of addendum to that, there's the self-replicating machine concept. I actually started with that concept, and most of the other stuff came as a kind of like a side, it's like a side effect. I've been obsessed with self-replicating machines ever since I first came across them when I was a master's student studying astronomy. I was fascinated by SETI and so on, and I wanted to get involved in it. At that time, it was not particularly a reputable thing to get involved with, but one of my professors at that time had been a colleague of Frank Tipler at Tulane University, and they'd written a book together called The Anthropic Cosmological Principle. So he pointed me to that. And one of the chapters in that, primarily written by Frank Tipler, talked about the SETI debate, now called the Sagan-Tipler debate, about whether extraterrestrial intelligence actually exists. And Tipler used an argument based on self-replicating machines, or von Neumann probes, they're sometimes known as, that the answer is no, that we have to be alone. And for me, who had been brought up with the Sagan view, I'd seen many of the Sagan shows. He'd done the Royal Institution Christmas lectures in the UK. He subsequently did the Cosmos series, which is very well renowned. And I was fawning, fan of Sagan. And then to come across this argument, it was like an epiphany, because it converted me almost instantaneously from a believer in extraterrestrial intelligence into an arch skeptic. So I determined at that time, during my masters, that I would do a PhD in engineering rather than astronomy, and that I wanted to figure out how to build one of these machines. Obviously, technology wasn't there at that time, so I specialized in robotics, which I saw as a key element to any kind of self-replicating machine. And so for many years, I worked on, rovers and manipulators in space and that sort of thing. And about 15 years ago, 12, 15 years ago or so, the 3D printing side of things mushroomed out. And that was my entree into, firstly, in-situ resource utilization, and secondly, self-replicating machines. So that's the history of how it all evolved. And it coincided with the kind of question I was asking myself again about 15 years ago, getting very concerned about what was the state of the Earth's environment, asking myself the question, what can a space engineer do to try and help with the situation? And so this led me naturally to solar power satellites.
And without asking you to spoil anything, kind of your dream of getting more towards clean energy with self-replication machines. It sounds a lot like the premise of your popular science title you're working on.
Well, yes. I mean, this is the primary motivation. The popular science title, Manna from Heaven, what I want to try and present in layman's terms, but also without shying away from the technical aspects, we have a problem. And the problem we have is that we're spewing out carbon dioxide, methane, and so on into the Earth's atmosphere. We see the results of this already this year, with warming. The US is affected, Europe is affected, the rich countries are now being affected just as much as the poorer countries around the world. But still, there appears to be this political impotence to really do anything about it. And I think the other problem is that although people say we know what to do about it, we know what to do about alleviating it. But I think we need something much more radical, which is to basically eliminate fossil fuel usage, apart from in plastics, of course. Eliminate fossil fuel usage entirely, and that really is the only goal that we should be aiming for. And if you start crunching the numbers, with wind and PV and so on and so forth around the world, you see that when you crunch the numbers, there are two issues that arise. One is the amount of land area they need to supply the amount of energy we require, and the second is that there's a metric called energy return on investment. So what this means is the amount of energy you need to extract to build these machines and then operate them, compared to how much energy they generate during their lifetime, and that includes disposability as well. And the numbers they're okay for the most part for that, but they're marginal in many cases. So most people are working towards what our current energy requirements are, which is about 20-25 terawatts. The problem with that is that our energy needs grow exponentially, and it doesn't look like there's any there's any kind of there's any leveling off of that. No matter what we do, we require energy. So if we want to mine nodules from the sea, that takes energy. It also disturbs ecosystems. And we look at the numbers again with the amount of land we're using compared to the amount of natural biosphere. We're consuming quite a large fraction of it, and it's destroying ecosystem services that we get for free. So when you look at these, our constant growth in energy needs, certainly a portfolio can potentially work with our current energy needs, but as our energy needs grow, it's going to stress the environment even more. So we need to think of something which is growable and clean. And to me, this, in a way, it's like saying that we have to go into outer space to the moon and asteroids and so on in order to preserve our own biosphere here on Earth. We need to bring energy in. We need to help the natural processes to bring energy to support ourselves. One could argue that we're a virus and that we should be eradicated. Well, I don't personally hold to that view because I think that's self-destructive and pretty horrible. Whereas I take the view that we do have energy needs. We are part. If you look at biological organisms, they're constrained by their environment. But our environment doesn't have to be constrained. We can go out there and actually create a larger environment and exist within that environment and still supply our energy needs. Most animals don't have that. Well, all animals except us don't have that option. And this is why we have brains to try and solve these problems. But we need to solve them properly. We can't do it by bit, little bit by little bit, here and there, with too many compromises. Because as long as we're spewing forth carbon dioxide, methane, and so on into the atmosphere, we're causing problems for us and future generations.
So it sounds like for you, this idea of self-replication and space exploration and sort of gaining resources from asteroids and solar satellites and all of this other stuff, it's not just something that's a cool and interesting research area. It's something that you think is essential for the future of humanity.
Yes, I do. I mean, it's cool as well. It's very interesting. There's no question. But I think it's essential. I think there is nothing. Going back to the Tipper argument, it's basically, I think this is something that any intelligent species is going to come up with this problem and have to resolve it in some fashion. And we can either tighten our belts. Now, you're American. I presume you're American. most Americans don't like anybody telling them to tighten their belts. So, it's also part of our nature to want to consume, to want to have whatever we want. We can argue about the rights and wrongs of consumerism and so on, but the fact is we do live in this world, and unless something horrible happens, like some kind of vast disaster or something, which nobody wants, then I think this will continue. And it has been a driver for most of human progress, rightly or wrongly. Greed has been the primary driver for most of human development, and I think that will continue. And I think we have to accept human beings as we are. We can't change who we are, but we have to ensure that we can live within our means. And I think SpaceX, self-replicating machines provides us with this mechanism for ensuring we live within our means.
And you mentioned it a little bit while you were talking, but if you're an engineer and you're interested in bettering the future of humanity, in my mind, there's sort of a variety of ways you can do it. You could look for better rocket fuel or look to build better solar satellites or things like that. What is it that has made you choose self-replication as the essential research area over, say, other research areas you could have chosen as the best investment in the future of humanity?
Right. Well, as I said, I came to it fairly elliptically. I never intended to. I had no interest in trying to save the world. A few years ago, I was just a space engineer who worked on interesting problems like rovers, and I was fascinated by astrobiology. I wanted to progress. I saw myself as a kind of an engineer who's focused on the astrobiology question, going to Mars, going to Enceladus and Europa and so on. And that's always been that's my bread and butter, as it were. But when I started asking the questions about what can a space engineer do, I had to approach it from the point of view of what my skills were. I couldn't re-educate myself as a kind of like an expert in wind generators or anything else like that. So I had to come of it from that. I mean, also to be fair, I was influenced by my history and my background, so it fell naturally to look at the self-replicating machine as a solution. And the more I looked at it, the more I became convinced that this was the right approach. Not just because it's an interesting problem, but because it potentially leads us to resolve some of our many problems in space exploration. It allows us to essentially to settle and colonize the moon and beyond at extremely low cost, because we send one machine there and it builds up copies, and then because it's a universal constructor, it can build anything thereafter. So you build the population you need for whatever purpose you need, and then you basically reprogram it to build whatever you want. So you can build moon bases, you can build other rockets to go to other planets. I focused on solar power satellites because I think that's something that potentially can have not immediate, but within a decade or so, an impact on our environment.
And I think, and you can tell me if this is right, kind of the key word in the advantage of self-replication is when you were talking about a lot of the problems humanity has with the environment, everything, you kept mentioning the word exponential. Our energy needs increase exponentially. This increases exponentially. Our problems in general increase exponentially as a civilization. And self-replication seems like it's sort of exponential by nature as a way to match whatever those exponential problems are.
Well, that's true. I mean, because you start. Everybody's familiar with this, the rabbits. 2, 4, 8, 16, and then you get this exponential growth in population. Except we're not talking about rabbits; we're talking about self-replicating factories, which can be relatively small, 10 tons or so, 15 tons or so. Yes, it's a different way of approaching mass production. So it's when we do mass production, we create very specialized machines and we produce lots of product. What we're doing here is we're creating a single product and we're replicating it in modular form, exponentially growing it. So it achieves much the same thing, but a lot faster and a lot quicker and more adaptively.
Absolutely.
What it does potentially enable us to do is things like petascale projects. When I say petascale, I mean truly enormous projects. potentially on a planetary scale. So, I mean, if you look at like Robert Ford's idea of trying to build an interstellar spacecraft using laser propelled sails, part of his vision was to have this very large Fresnel lens in the outer solar system, 1,000 kilometers in diameter or so. Well, the prospect of building that at the moment seems ludicrous, impossible. But this is the kind of petascale project I'm talking about. If we break it up into modular pieces, we could use self-replication as a means to rapidly construct something like that. And so it does introduce this possibility of doing things on an enormous scale, including, for example, geoengineering. So, for example, if you want to put a Fresnel lens in the Sun-Earth L1 point, we potentially could do that in a modular fashion, and then potentially cool the Earth in a way that doesn't interact with the Earth's biosphere, where most other geoengineering schemes do interact with the Earth's biosphere. And also the shield, of course, can be switched off by simply turning it like a Venetian blind. So it provides us with the opportunity to do things that we just couldn't imagine. If we look at, for example, going back to the idea of the solar power satellite fleet, I calculated that to power the Earth's energy needs purely using this mechanism, we'd need a geo-ring about 1 kilometer wide. Now, that's actually relatively small. You couldn't see it from the naked eye from space. It's very far away. But potentially that could grow. And gradually as it grows, it provide more and more energy. And one can see the obvious limit to that is that potentially create some kind of Dyson sphere around the Earth. Not that I would condone such a thing, but certainly that's a logical limit to it. But yes, it provides us with a mechanism for growing our supply with our demand.
Absolutely. And the way you have to think about self-replication, I'll tell you, a while back, I got very interested in supply chain management academic papers.
Oh my God, how'd you get into that? It sounds frightfully boring, but anyway, okay.
I had a friend who was into supply chain management, and he said, I said the same thing. I said, that sounds very boring. And he said, no, it's really interesting. So I started reading it. And what I was actually going to say is that the way they approach problems in supply chain management reminded me of a lot of the way that you approach problems in your papers, because it's kind of this idea of, all right, we've got this final product, and we need this final product is made of these 3 pieces, and then each of these pieces is made of these things, and each of these pieces is made of these things. And we need some sort of sustainable, semi-autonomous set of events that goes from raw materials, so sort of moon rocks and moon metals and things like that, to a self-replicating robot. Yeah, would you like to kind of speak on the way your work might be a little bit different from sort of standard engineering work in that way?
Sure. Basically, the biggest difference between a standard product, if you're creating a factory to create a product, is that the machines of production are themselves the product. So that's really the first thing you have to understand. Now, obviously, the more complex your machines of production, the more complex, the greater the number of raw materials you need to create that product. Like a mobile phone, for example, you look at a mobile phone, you've got about 60 different materials in there. And they all come from all around the world through this massive, very complex supply chain. Now, admittedly, obviously, at the mining level, they supply many different industries and so on and so forth. But from our point of view, we're focused on the product. And so what we need to do is figure out what goes into that product to make that product. And then when we look at the product, we have to figure out, well, if we want to create, if that product is the machines of production themselves, then we have to try and minimize that, because otherwise we'll end up with a situation where we can't close that replication cycle, because it requires too many different materials. We have, for every single, let's say, for example, you want molybdenum, you have to have a whole process of mining that molybdenum and then purifying it for just one tiny piece of an alloy. Now, does that make sense? And my answer would say no. I would much rather work with an alloy which maybe isn't quite as optimized, and we can adjust our design to compensate for that by eliminating that part from the supply chain. And so what we were trying to do, we're trying to narrow this fan in into that we require to create the product. And we want to do that all the way along the manufacturing chain. So we want to start off with materials. We want to minimize the materials we require to build the product. So this means exploiting some of the multifunctional aspects of materials, like aluminium, for example, can be used for many, many different things. And we say, well, okay, we're going to use aluminium for all this sort of stuff. And so, for example, an example would be instead of copper as a conductor, we use aluminium. So we don't need copper anymore. We also look at various alloying additives. Now, if you look at the moon, on Earth, for example, we need additives to reduce corrosion, oxidation, and water, susceptibility to water. We don't need that on the moon, so we can eliminate those quite easily. So that, for example, we don't need chromium for that, which is used for that purpose. So we could start to simplify things which are suitable for the moon or for asteroids, and start to create a new set of materials, alloys, which are suitable for that environment. And they may not have the full functionality of some of the materials that we require, but they will offer some of it. And we change our design accordingly to either increase the amount or whatever to implement the function to the desired level that we need it. And we work all the way along the manufacturing chain to look at this. So we're looking at, so that resolves the mining issue. Then we look at things like manufacturing. There are many different types of manufacturing processes, wire extruders, lathes, CNC machines, 3D printers. So in trying to minimize the number and types of manufacturing machines you want, 3D printing is actually ideal because it's actually very versatile. And potentially allows us to produce things that you can't produce in any other way. So I focused on 3D printing as a potential mechanism for creating a universal construction mechanism. Now, it may be that in some circumstances, it won't be able to quite fulfill that requirement. But we can imagine how we might be able to add additional heads to it. So you can add a milling head inside the machine. So it's a part CNC machine, part 3D printer. So we could start to create a single unit machine which can do many things, and hopefully eventually produce everything that we need. So it's focusing on these kinds of technologies, and many of them are kind of like current research areas. So, for example, this type of 3D printer, it has to print in plastics, it has to print in metals, it has to print in ceramics, and it has to print in glasses, and so on. And trying to and they all have different thermal regimes. And so we have to figure out how to deal with those difficulties and thermal regimes. And this is something we've been working on. For example, we've successfully melted aluminium alloy onto silicone plastic, because silicone plastic is highly resistant to temperature. So that's a way in which we can look at, combining in the same machine the extrusion of silicone plastic in conjunction with the printing of metals.
Would one of the advantages of this approach of creating a sort of a universal construction machine, would one of the advantages be that you could update your design for whatever your self-replicating thing is remotely if you wanted to?
Yeah, it's the perfect machine because I think I said in one of my papers, actually I got this idea from Frank Templer, is that it's a machine which can never become obsolete because you simply upload the new program and it prints its new offspring. So it never becomes obsolete. And so your development, you don't have to fly a new machine to the moon. You just basically upload the new program and it'll print the new machine for you. So yes, it provides that capability, and you can imagine. A lot of people talk to me about, can we use this on Earth? Yes and no. The hard part is actually the problem with the Earth is that it's tectonically complex. So we have ores concentrated in certain areas. We have if you want, I don't know, coltan, you have to go to Congo or something like that. And this And this creates a problem for a general self-replicator. The moon is not so much a problem. It has a relatively simple, I say a relatively simple geology in comparison to Earth. It's relatively homogeneous, or at least partially homogeneous. So that makes it easier from that perspective. It forces us to deal with what's there, but at least we can design for what's there. It'd be difficult for Earth because, if I'll give you an example, let's say selenium. Selenium is we use in the self-replicator as a photoactive component, photoactive material. Now, if you live in North America, you're lucky because there's quite a lot of selenium in the soil. If you live in China, you're not so lucky because there's much less selenium in the soil. So we would have to adapt our self-replicator to deal with the individual environments in which we found ourselves. That actually is quite challenging because you then have to redesign the entire self-replicator to accommodate that. That, to me, that's something that we'll deal with at some stage in the future. I'm just trying to get the damn thing to work, so...
That's sort of your PhD student problem at some point.
Yeah, one day, yeah. Not at the moment. I'm focused very much on the space exploration. I've actually managed to spend most of my career actually pretty much exclusively on space work, and I've never been attracted to the dark side of doing things non-spacey. So,
very interesting. And what you were talking about with the idea that it can build the better machine, I was reading about Voyager recently, and it was amazing to me that they've been able to push software updates to it consistently over the years. But part of the issue is that the software can only do so much because the hardware is the same as it was when it was made. And so your universal construction machine is sort of a way to get around that issue.
Yeah, and in fact, I was at the Interstellar Symposium actually just a couple of weeks ago, and I made the point that if we want to send an interstellar spacecraft to another star system, there's several ways we can do it. We can do it this like the breakthrough starshot way, which is to basically have lots of tiny, very simple spacecraft and use this laser to propel them, scattershot them through the cosmos, and hopefully one or two of them might get to the location and send back some pictures. That's one approach. But if we want to do a more directed, more focused approach to get more information from the location where we're going to, let's say we're going to Proxima B, for example, I'm sure most people would be very interested. Rather than getting a sort of like a blurry snapshot picture, I think most of us would think, well, we'd like to get something a bit more substantial than that. We'd have to invest in a more complex spacecraft. Now, if we, there are a lot of people working on propulsion systems and so on and so forth. I'm not going to go into that. My view is that if you look at something called system availability, it depends on three parameters. One is the mean time between failures, so that, between components. So you want to lengthen that as much as possible, and this is what we call reliability, high reliability components. But that will only get you so far. We have no experience in building components that can last 100 years or so. Most things that we build will last for, well, apart from structures, but most things we build with any complexity will last a maximum of 20. So we're going to have to readdress this idea of how to make the spacecraft reliable. We want it to be functioning when it gets to its destination. We don't want it to be sort of like crippled and not working, or, nothing, otherwise it's a waste of time. So the other two ways of dealing with this is to have a supply. You can have a supply of components on board. And in fact, this was the approach of the Daedalus starship from the 1970s. They had wardens on board, which would basically go out around outside and fix things and replace components and so on. And that's one approach. But I think a more robust approach is to have that as well, that servicing capability. But also, there's the third component of availability, is mean time for supply. Now, this implies that you get your supply of components from somewhere else, whereas we're talking about building it on board. So we can adapt 3D printing as a mechanism to build on demand whatever components we need to replace. Now, this requires us to have a certain amount of either pre-built components, which we wouldn't have, we wouldn't want to do because you'd end up too many of the wrong components and not enough of the right ones. Or we build on demand, which means that we have to have the raw materials to build them. So this goes back to my argument that really we want to narrow down when we build our spacecraft, we want to narrow the number of materials it's constructed from. So essentially all we have to do is supply, let's say, 500 kilograms of X, 500 kilograms of Y, 200 kilograms of Z or whatever, and we can mix and match them and put them together to manufacture whatever component we have on board. Things like, annealing and things like that. So basically, and also, we also have to have the components required to build the actual machines themselves. So to repair those, because if we bring machines of production with us, we have to be able to repair them. So again, this comes back to the whole idea of self-replication in many respects. But the point I'm making is that when we design the spacecraft, we have to ensure that we build with a minimum number of materials, and we can carry a set of feedstocks of those materials from which we can build anything on board. And so my view is that when we do start to build starships, what I see when I say starships, I mean robotic starships, they will be partially self-replicating already, because they'll have to be able to, self-repair. And self-repair, of course, is a subset of self-replication. So I think that when we start to build practical starships, we're going to be forced to go down this route.
And this idea of sort of feedstock and the materials you have to build something out of, it gets to an essential idea that gets brought up in almost all of your research called a demandite. Would you like to talk about what a demandite is a little bit?
Yeah, the demandite was originally developed for the moon. But yes, we have, if you can imagine a spacecraft, it has various subsystems on board. You have, propulsion system, attitude control, whatever, and everything, avionics and so on. Now, those are the basic subsystems. Now, within those subsystems, you have certain components which are fundamental. So, if you look at thermal, you need to have something which can conduct heat well. You need something which is an insulator. You need something which can, if you're talking about active, you also need something which can radiate heat. And so all these functions are required for a thermal control subsystem in the spacecraft. We can implement, most of them are actually based on material functions. So a radiator is a highly polished aluminium surface. A thermal conductor is something which conducts thermal energy well, basically a thermal strap. And again, an aluminium strip will serve perfectly well for that. Insulation, well, most insulation, you can either look at MLI, which is a very complex form of insulation, or you can look at something fairly simple, like glass fibers, which is used a lot for insulation, and which is a lot of thermal insulation is in fact just glass fiber. If you look at heat shields, they are basically silica fibers. So again, we can build a lot of this functionality that require for any particular spacecraft in general, and we have to make it. And the demandite list started off with these are the functions we require of various materials, and on the other side of the column was basically this is what we need to extract from the moon to implement these particular functions. And so that was where the demandite come from. It was basically looking at the functions required to build any kind of spacecraft and look at the various materials that can implement those functions. Maybe not optimally, but at least they can function in some fashion. And of course, on the moon, we're not constrained by the constraints on normal spacecraft design because weight is no longer much of an issue.
Very interesting. And I like that idea of a demandite. It took me a little bit to wrap my head around, but
right.
It's a very clever idea once you sort of get it as a way to understand and think about these things.
Well, it kind of came from my background as a spacecraft engineer. I've worked on spacecraft design for many years, and so I understand, what each component is and what they do on board a spacecraft. And I used to be at Surrey Space Centre, so when I was at Surrey, they were well known for building the first small sats. And again, they're very simple. The small sat concept was do things as simply as possible, use minimum cost, and basically put all your complexity into your software to extract maximum functionality out of it. So, and in fact, I believe it was Surrey who first developed the notion of using COTS computer hardware and then implementing error detection correction coding to compensate for its greater susceptibility of radiation. So this was an approach which at that time was, NASA had gone down a specific road of hardening electronics, whereas Surrey had taken a different route. And now this is quite common. This is fairly routine now.
Very, very fascinating. Moving a little bit away from sort of the generalities of your research and more to some specific ideas. An idea you told me you were just starting to think through that sounded very interesting was building Earth return vehicles to ferry rare earth elements from the moon. Would you like to talk about that a little bit?
Yeah, this actually follows on from what I was talking about with silica fibers. Silicon fibers. Silica fibers. Yeah, it actually goes back to two things. One is when we look at a northite, we've been actually doing some experiments in extracting various elements out of a northite. So we're using something called HCl leaching, which we've demonstrated in the lab. And the first phase actually basically precipitates out silica. And the second stage then extracts alumina, which we can then convert to aluminium and so on. But let's focus on the silica. So the silica can be used in various ways. We can convert it into quartz, for example, to create a piezoelectric material, which can be used for sensors. But more interestingly here is we can use silica to create glass fibers of various kinds, or glass or silica fiber, pure silica fibers. Now, silica fibers have been used for heat shields for many years. Virtually everything is a variation on this concept. I think now looking at different types of plastics, but let's focus on silica. And we have a plentiful supply of silica on the moon. So potentially what we could do is we could manufacture heat shields on the moon relatively straightforwardly. It's just basically a structure that you put in a cap onto your payload part. The other aspect is that we know that there are rare earth materials in certain locations, protoselenium basalts and so on, which are enriched in, they're so-called creep materials, KREEP, K meaning potassium, Re meaning rare earth elements, and then P meaning phosphorus. So when they say they're elevated, these kind of minerals are elevated in creep, they're elevated in creep in compared to the rest of the moon. They're not elevated in creep compared to Earth. Earth still has quite high creep, rare earth element proportionality, but it's fairly diffusely spread around the Earth. There are some locations which are slightly higher than the other. Most of them are actually around China. So this is why they tend to have a control over the rare earth element industry. And also their attitude that they tend to have less benign restrictions on environmental degradation than we have. So obviously rare earth elements are extremely important for supplying things like magnets for wind generators and pretty much any type of motorized system. And so they are very much in high demand. If either China, for one reason or other, needs or wants to limit this supply to the global market, which I can understand why they would want to do so. They want to protect their own markets, their own needs. Then it provides a bit of a problem for everybody else. Now, I believe there are various potential rare earth element mines in the US and in Canada, but we are constrained by extreme regulations on environmental degradation, which make them very expensive. So it may become the issue that if we could develop a second generation of ISRU technology on the moon, where we could extract rare earths from the moon, and then we can package them into these, into these capsules with these heat shields manufactured locally. And then essentially what we'd do is we'd basically, send that to Earth by whatever means. I tend to favor electromagnetic launches because it's basically a renewable energy approach. Send them to Earth, and then they'd basically enter Earth's atmosphere, the heat shield would ablate, and they would land, I don't know, either in the ocean, depending on how many parachutes you want to use and so on, and be recovered from the capsule. The only thing that's really consumed in this process is the heat shield, and of course we can manufacture that on the moon ad infinitum, effectively. So this provides us with a mechanism for a relatively low cost, creating a supply chain from the moon to the Earth of rare earth elements to Earth. Obviously, the devil is in the detail. But what we'll be looking at initially is the silicon, the heat shield part, and looking at the process of extracting the rare earths itself. Presumably we can manufacture most of the rest of the spacecraft from the self-replicating machine concept anyway, because that's built around the demandite issue, the demandite concept. So, yeah, this is a development of that. We'll be looking into that in the near future.
And one of the things you mentioned in a few of your papers is the idea of basically a orbiting set of robots that go around the Earth that sort of build things in orbit around the Earth. Would that be a way to make this even cheaper? Would just be to put the rare earth elements directly into orbit and assemble things with them there, as opposed to sending them all the way to Earth?
I guess, yes, actually, I hadn't thought of that, actually. I'd seen the two things as independent. I think what you're referring to is some kind of space manufacturing facility to deal with debris. Yeah, okay. Yeah, that was another thing we were looking at. I hadn't put the two together. I'd assume, well, given that we can manufacture the heat shields on the moon, so what you're suggesting is maybe we could add value to the rare earth elements before we put them on Earth, send them to Earth.
Yeah, something like that, or we could sort of package up the two together, disassemble.
Yeah, I guess. I mean, I hadn't thought about it, but yes, I guess what we could do is basically send the rare earth elements to the space manufacturing facility with the heat shield. The SMF then basically converts the rare earths into magnets on demand, fully manufactured magnets, which we've already done with 3D printed. Well, we didn't. Oak Ridge National Laboratory 3D printed magnets for us, and then basically bring that to Earth as ready-made, value-added products. Yeah, that could also work. Actually, probably the economics would work even better. Actually, with that. Yeah.
And speaking of economics, one of the really interesting things about all of the self-replication research, and I guess sort of looping all the way back to Star Trek, is it seems like in terms of the amount of product you get for cost, where we send one self-replicating thing up to the moon, and it's the cost of building that thing and sending it up to the moon, and we get sort of 1 million self-replicating things if we wait long enough. Yeah. It seems like that's, as far as your futurism goes, that's a very big step towards building a post-scarcity society, almost, is being able to produce that much for that little of a cost.
Yes, I mean, but the cost model is built on the notion that it would be automated, not involving people and astronauts on board the moon or whatever. But yes, if we can, I mean, this is where AI fits in to a degree. If we can automate this entire process, we basically have a box, and it's a magic box. And basically, you put in material. You basically say, hey box, I want you to build this, and the box will come back and say, I need X amount of soil, and you put an X amount of soil in, and then things happen inside, and out pops your product at the end of the day with some waste at the end of it. So ultimately, this is what we're trying to build, is this kind of capability, is this box. And not only that, this box can build another box, and you can give that to your friends and say, hey, I'll give you this box. And then that person can say, oh, I'll give that to my friends and a couple more and so on. And I had this vision actually a couple of years ago, of if we could do this in Africa, build a self-replicator in Africa. And of course, this means also it builds its own energy system as well. So it supplies energy. You could have this bot, everyone, once you send this box there, then this box, then people create the boxes for their friends, and they send their boxes out. And so I calculated that you could basically industrialize. When I say industrialize, I mean industrialize not in the way that we've industrialized historically in the West, but personal industrialization. So industrialize family by family, provide productive capacity to each family in Africa within a decade, which would be astounding, because it basically provide people, every family would have a self-replicator in their backyard, or whatever yard they might have or whatever. And they could supply all their own energy, and assuming they got, access to physical resources, then they could build pretty much everything they needed, including their energy supply. So, yeah, I think the potential for this concept is really quite remarkable. And I think it's limited only by human imagination. I mean, I've just thought of a few things myself. I'm sure other people will think of other things that they could do with it, which would be great. I think the power of this technology is just immense. And I think we've only just scratched the surface of its capabilities, if we could develop it.
What a beautiful dream.
Yeah.
It's the world I'd like to live in. Very cool. And as kind of the last point of discussion, you told me about this other idea that's also in development, which is to build electromagnetic launchers on asteroids to get tuna coast resources to the sort of lunar factory that you're interested in building. Would you like to talk about that a little bit?
Yeah. This was actually derived from a paper I wrote a while ago. I wanted to look at what the self-replicator could do for asteroid mitigation. And so I crunched the numbers, and I found that if we could build copies of, if we could build the self-replicator a certain number of times, and then it would devote itself to building electromagnetic launchers. And I calculated how long it would take and how long launchers would have to operate in order to consume the entire asteroid. So it came up to, I can't remember the exact, I think it was a couple of months or something like that, 2 or 3 months. And the advantage is that with the self-replicator, because you adjust it to the size of the asteroid, there's a logarithmic relationship between the time consumption against the mass of the impactor. So the size of the impact does, the time grows only logarithmically with the size of the impactor. So it still keeps it within in less than a year, no matter how big it is. Most other approaches require 20 years sometimes. I think gravity traction requires about 20 years or 10 years, depending on the size of it, to shift it a little bit. Other ones also are potentially dangerous, things like impactors and so on and so forth, nuclear projectiles and so on. So I thought this was actually quite it's a potentially useful approach, because it can react to individual asteroids, adapt to individual asteroids quite easily. So after that, I thought, well, instead of consuming the entire asteroid, why not deflect it and move it to wherever we want to as a resource? Essentially, turning a sword into a plowshare, I suppose. And so I've started thinking along these lines about how we might want to move a nickel iron asteroid to actually even a carbonaceous chondrite, because carbonaceous materials are very rare on the moon. So we could potentially move a carbonaceous chondrite to the moon to provide a source of carbon and other volatiles. But I've been focused primarily on the nickel iron, mainly because this is a source of nickel, iron, cobalt, tungsten, and potentially selenium as well. These are actually quite, well, apart from the iron, these are actually quite rare on the moon. And there have been some studies looking at past impactors on the moon, and shallow angle impactors potentially could have produced, well, we assume have generated buried resources of nickel iron on the moon beneath the surface. We haven't found them yet, but certainly models suggest that they are there at some undetermined depth. So I've made the assumption that they are there in my self-replicator, but if they're not there, then we got a bit of a problem. So we have to then try and make our own impactor to move a nickel iron asteroid onto the surface of the moon. Well, we could do an impact, but the problem with that is that it's uncontrolled. It's create all kinds of havoc and everything else. So why not soft land one of these asteroids onto the surface of the moon? So the idea is to maneuver it into a low lunar orbit, maybe 100 kilometers altitude, and then basically descend it to, well, we could do it in various ways. We could do a nullifying descent where it drops, say, a few hundred meters height, or we do a complete soft landing. There are various degrees in between. So this is something I'm interested in looking at, is, the idea of implementing electromagnetic launchers which consume the asteroid as it's maneuvering it, but obviously they're consuming this very small amounts, but we'll end up with a significant fraction, a huge, great nickel iron ore body on the surface of the moon, which can then mine to provide us with our, nickel, cobalt, selenium, tungsten that we need.
And would you be, I believe these are both electromagnetic launchers, you can correct me if I'm wrong, would you be using like coil guns or rail guns for that?
Well, it's interesting about that. I've assumed coil guns. We built coil guns in my lab. Obviously, they're kind of like they're kind of like student-built projects. They're not optimized or anything. And so I've assumed the coil gun, primarily because of several of the disadvantages of the rail gun. Things like high friction and so on and so forth, and wear and tear. However, somebody who was in contact with me a while back, I can't remember, has reasons to think that the coil gun can't get the exit velocities that you can get from a rail gun, and the coil guns won't get sufficient exit velocity to exceed the moon's gravity. That's something we'll have to investigate. Whenever somebody tells me something can't be done, I immediately try and do it. So it's one of those things that I see that as a challenge. When somebody says something can't be done, I'm afraid it has to be.
What a good engineer. Are there enough asteroids that fly close enough to the moon that this is sort of a feasible plan or something that's worth doing?
It doesn't really matter, to be perfectly honest, because you're consuming the asteroid itself to get you there. So the delta V is still going to be relatively small, even with I can't remember the numbers, but I mean, I'd imagine a delta V of something like 3 kilometers per second, which is fairly large, I think, for a maneuver. That should be achievable. Well, and again, it depends on the mass of the body you're moving and how many EM launches you're doing. Again, this is one of the things we'd have to look at, see if there are any boundaries. But instinct tells me that there shouldn't be.
Very interesting. And you mentioned that you would be looking to do this with stony iron asteroids. Would you be looking for like pallasites or mesositerites or both of those?
I haven't gone into that level of detail. Again, I know I was mentioning stony irons, but that when I mentioned stony irons, I think I was focused on the self-replication process. So we need to have the silicates for the self-replication as well as the metals. The goal is to have something which is what we want to get to the surface of the moon is the metals, the iron, nickel iron. So that would be the payload element. and we'd need some of the iron, the nickel iron, and some of the silicate material for the actual building of the infrastructure itself. There's the coal guns and the self-replicator and so on.
Very, very fascinating. Well, this has been a wonderful discussion, and I'm almost sad that this isn't a 4-hour podcast. Before we, because I could just discuss all of this all day with you. Really, really fascinating. Before we end off, do you have anything that you would like to promote or tell people about or anything like that?
No, well, other than that, please shout the praises of self-replicating machines around. I don't think enough people understand it. I don't think enough people really know about what self-replicating machine can do. When I talk to people, if they're not familiar with the concept, they're kind of like a bit confused by what it means. So if you believe, I believe that self-replicating machines is the way to go for future space exploration, in whatever shape or form that we want to do it. So, and if you're convinced by that argument, then you should be telling everybody about it, saying, this is what we should be doing. And at the moment, I feel like a lone voice in the wilderness. It's like shouting about the Messiah or whatever, and nobody's really listening. And but I'm convinced that this really is the only approach for a robust space exploration strategy. I think this is the only robust way to do it. And the spin-offs from this would just be immense. And I think it's something worth pursuing. And, the more people I want people to pursue it independently of myself. I want other people to be working on this as well.
Well, you've certainly convinced me that this is the key technology for the future of humanity. Thank you so much for being willing to be on the podcast, Dr. Ellery.
It's been a pleasure, Daniel. Thank you very much.
I hope you enjoyed that episode. If any of the discussion piqued your interest, I have a page on my digital garden dedicated to providing a point of entry for anyone who wants to explore these topics further. It includes work from the interviewee, sources for anything that was mentioned in the discussion, as well as my personal notes and resources that I put together in my preparation for this episode. The link to that can be found in the description. Finally, I am proud to do this podcast as a member of Florida Atlantic University's Machine Perception and Cognitive Robotics Lab and Florida Atlantic University's Center for Future Mind. Thank you for listening.